Okay, so if I say cousins, what comes to mind in this class?
What is that?
Cousins?
Light ray.
Radiation, yeah, different radiations, exactly. And one of the things astronomers do is to look at different radiations. Sometimes they say different wavelengths of light. Actually, this is a picture we're going to come back to, and this is looking at microwave radiation. Microwave. So what do you think? Do you think long wavelength, short wavelength, microwaves? How many people think long? I think long wavelength, yeah. So it's pretty long wavelength. And it is such a cool story. These guys actually, Wilson and Penzias, I think it is, actually earned a Nobel Prize in, was it physics or chemistry, for seeing this signature. This is a signature of the birth of the universe, not the birth of our galaxy. Looking in microwaves, okay? So how's that for you? I know. So BB stands for Big Bang. And sometimes people will say it was neither big nor was it loud. Because I've already kind of been alluding to this singularity, which, I mean, we think of black holes as being very dense, but the singularity that contained all the matter and energy that was going to become our universe. Like, are you serious? So it's very small. And one of the things about sound, and I talked to one of you guys about this recently, one of the things about sound is to hear something, guess what? You need medium. You need material for sound to propagate through air. So one of the things is if you're in outer space and you scream, that scream's not going anywhere. Okay, because there's no particles, it's a vacuum to carry the sound. That's a whole nother topic. It's so interesting. So the Big Bang, okay, what physicists, astrophysicists, scientists do is basically look at what we got today, and one of the things they look at is what the galaxies are doing, that acceleration of the galaxies away from ours and all that, and basically they step back in time. And they apply the laws of physics, the laws of the universe today to go back in time to understand what the deal was with regard to the Big Bang. So we've done a lot of charts in this course, okay, a lot of graphs in this course. Let's look at what this graph does. Now, we talked a little bit about scientific notation. How do I say this? Let's see. What if I were to say, now this is seconds, okay, 10 to the minus fifth 1 times 10 to the minus fifth seconds. That is 0.00001 seconds. Okay, 10 to the minus fifth seconds. 10 to the minus 45th seconds. That is 0.
This is gonna take a while.
1920. Okay, something like that. I might be off by 1. Okay, but it's that fraction of a second. Okay, it's that fraction of a second, and I'm going to go ahead and right here, I'm going to write BB for Big Bang. That's how you read this. Right there, oops, right there, is BB for Big Bang. So that's how you read this. The Big Bang happened, okay, that fraction of a second, that fraction of a second, that fraction of a second. Now right here, do you guys get this? Okay, so this is actually 10 raised to the 0th power. 10 raised to the 0th power is what?
1 second.
1. Yeah, 10 raised to the 0th power is 1. So this is actually, like it says, this is 1 second after the Big Bang. Right? And what did we say? You guys have a test question. How old is the universe? About 14, 12 to 15 billion years old, exactly. Now, all right, this is kind of interesting. So 4 times 10 raised to the 17th power of seconds is how old the universe is. Do the math.
Okay.
Factor label. I know, Jay wants to go do the math. And I'm not sure, this is probably dated. It could be, maybe 3 or 4 or 5 years ago. But that's how old the universe is. So I kind of want to put in perspective from the 1 second to over here is, what did you guys tell me, 14 billion years. you guys been with that? So that's kind of how this works. I know, right? It's a power of 10 along the x-axis. That's what's throwing us off. Okay. So what's along the y-axis? Temperature. So what do you think? Back at the time of the Big Bang, was it hot or cold?
Really hot.
It's really hot. It's really hot. And it's been cooling down ever since. It's very hot. 10 to the 32nd Kelvin. Okay? So here we go. This temperature right here, we got time, is 1, let's see, I'll just do this. 1, and then I need to do 30, I don't want to do a comma there. 1, 2, 3. 15.
It was really hot.
30. Okay, that hot. That was how hot it was. Yep. And it's been cooling down ever since. And if you're like me, you're like, well, what is this temperature here now? Okay. And actually, that's a good point. But if this is Kelvin, if this is a Kelvin temperature scale, what's the coldest temperature on the Kelvin temperature scale?
200 and I think 83.
Negative 273
Yeah, that's what I
Celsius.
said.
Negative 273 Celsius, but what on the Kelvin scale?
Oh,
0. Yep. What happens at 0 Kelvin? Absolute 0. All matter stops moving. So anyway, that's kind of the cool down of our universe. That is so cool.
Wait, do you think it's going to go to the universe will eventually reach here?
Well, that's not what I'm gonna. That is actually one. That's one possibility.
Heat death.
Yep. What was I gonna say? Oh yeah, I think what I was gonna say was the thing about matter. If you're going this hot, matter cannot stick together. Matter is crazy out of its mind, right? And so one of the things we're going to see as our universe went from the singularity to the universe we know and love today is the cooling was very important. Okay, so that's my point. All right. So Einstein said E is equal to mc squared. What is C in E is equal to mc squared?
Speed of light.
The constant, the speed of light, exactly. And what is the capital E? Energy, yep. And M stands for, I think I'd go with mass or matter. It's like the mass of the matter. So what Einstein said is you can get energy from matter and it's related to the speed of light squared, like this. Okay. So early on, and in chemistry we do a lot of like the arrow, so like, you know, we do reactants go to form products, like this. Reactants go to form products, right? Kind of from left to right, we write chemical equations. Well, if you see something like this, where it actually doesn't go from left to right, but it also goes from right back to left again, that means it's a two-way street. There are a lot of things in chemistry that actually does it. It's called equilibrium. So at the time that our universe unfolded, the Big Bang, actually it was very chaotic, and you had very energetic, thus the heat. So you had basically energy going to form matter and matter going to form energy, back and forth. Okay. So this is kind of showing you, let's see, this is kind of from left to right. Those little squiggles, can you think gamma ray photon, does it seem like energy? Energy going to form matter, and here we have matter going to form energy. Energy going to form matter, and matter going to form energy. Okay. Now that's not normal matter to us. The whole, well, I guess it is kind of normal. Well, the electron is normal, but the anti-electron is not. Okay. Now this is kind of, and I'm going to try to bring up some videos to prove you, because if you listen to it in a video, you'll believe it. But it's like Star Trek says, the whole antimatter and matter. I mean, that's a real thing. The whole antimatter and matter thing. I know. And kind of related to how do we know the matter thing and the antimatter is a real thing. I doubt if anybody's I've never been to France. Have you been to France?
Nope.
No, not yet. Okay, and this would be Paris, the city of Paris. I think it's outside the city of Paris, maybe. But can you see these kind of hinty, these circles there, kind of superimposed? What's that?
I see one big circle.
One big circle. There's kind of a bigger circle and a smaller circle. Yeah, there's two circles, and I was just noticing that today, and I didn't check it, or last night as I was getting ready for lecture, and I didn't chase it down. But to me, it almost looks like they have two tracks. That's a track. And you can kind of get a sense for how big the track must be because of the city, right? You can kind of see the city there.
That's a hydron plotter?
Yep, it's a large hadron collider, yep. So here's what they do basically, is they start right here, okay, and they send something this way, and they send something this way. So they go whoop, okay, and I'm pretty sure they maybe send it, maybe a couple passes, they can channel it where it goes. So maybe it goes a couple passes, it misses, okay, then it misses, it's accelerating, okay, it's called a particle accelerator. So accelerated particle, and then all of a sudden they're like, all right, you're fast enough, boom, we're gonna let you run into each other. Isn't that cool? And I've heard on videos where they describe it kind of like, if you wanted to know the way a car was built and you were gonna be drastic about it, you might go ahead and take two of your cars and let them run into each other and look at the pieces after, you know, and try to kind of make sense of it. I know there's other ways to understand what a car does, but that's kind of drastic.
Jesus, there has to be a better way.
Well, when it comes to particles, this is kind of what they do. So this was actually, when it first came online, or kind of the technology was first being used, and I'm not sure that they're out of the woods yet, but they worried that once the particles collided, it would have sufficient density actually to create a little mini black hole. So, I mean,
That hasn't happened.
only in the science fiction movies. Right. So when we talk about particles, you know, electrons, we're good with that. Electrons, we're probably good with protons, we're probably good with neutrons. Those three are things in chemistry we worry about. You know, protons and neutrons and the nucleus and electrons, that's normal matter. But there are more exotic things than that, and these, the Large Hadron Collider, is a way to get to what the smaller particles are. So, which in chemistry, I really don't care about the smaller particles. The three ones bend my mind enough. So I mentioned that we kind of look at what our universe is today, and we kind of have to do, well, physicists, when they try to go back in time to the Big Bang, have to kind of piece things together based on what they observe now. So these four forces are what we observe now. These four forces are what we observe now. I'm going to kind of talk you through what they think, how these four forces came to be after the Big Bang. Gravity, we kind of all got a handle on gravity. We talked about gravity. We do, but we don't. You know, if you do much reading about it, the jury's out a little bit in how it works. We know a lot about specifically mathematically how it works, but the crux of how it works. So gravity is two objects that have a mutual attraction for each other. Gravity can be explained a lot if you talk about the fabric of space and time, kind of the dents that are created by the objects. Electromagnetism, that actually comes to me, when I think about electromagnetism, you think about positive and a negative charge, and then they're attracted to each other. Actually, if you look at an atom's all about that, because, you know, you have your protons in here, maybe some neutrons, that's my nucleus, you guys would tell me, and I have electrons outside the nucleus, that's an atom. And so that electromagnetic attraction between the electrons and protons, for example of electromagnetism.
Is that like kitchen magnets?
Yeah.
Are they
Kitchen
undergoing
magnets.
that same?
Yeah, kitchen magnets would be doing the same thing. It's ferromagnetic, and that's why they do what they do. So, yeah. Yep. And then the other two are more into the workings of an atom itself, even more than the electromagnetic force. The strong force works only over a short distance, and it binds the atomic nuclei together. So remember what's a nucleus? Center, yeah. And this is my electrons. This is my nucleus, yep. And so in the nucleus, we have protons and neutrons. Now, one of the things about those protons in the nucleus is protons plus protons don't like to coexist. They don't like to be. So we have this binding energy. So that's kind of where that comes from. Then the weak force, actually, my notes up here say something about if we have some sort of fusion or fission going on, like in our sun, it's fusion. Hydrogen plus hydrogen goes to form helium, okay? Actually, it's this force that's associated with, you lose a little bit of mass and you create energy. All right, so four forces we have today. There they are. So here on the next few slides, we're going to talk about those four forces. But at certain points in time, and we're going to see that they are, when I say certain points in time, remember a little bit ago we said that the Big Bang was over here, and then we had 10 to the minus 45th seconds after the Big Bang. I mean, back in time means just a fraction of a second after the Big Bang. What they think, or what we think, is that the current day weak force and electromagnetic, actually used to be one force called the electroweak. It kind of makes sense. Electroweak, electromagnetic, and weak force. Okay, going back in time. And that actually, even more back in time than that, the electroweak, which is electromagnetic plus the weak force, and the strong force were all combined. Now, which force wasn't part of the gut force? Gravity, very good. Gravity was the outlier there. Yep, exactly. So kind of related to that, gravity was the outlier. If you go back even further in time, and I think Einstein was looking for this universal force. Is that what it says? Okay, super force, or universal force that has all four of them. The gravity, electromagnetic, strong, and weak. Okay, but that would have been even closer to the time of the Big Bang. So now this one, and I kind of apologize, but this is what your textbook does. I think I'm going to pull up a blue color if I can. Where's my blue? This one is opposite of what we last looked at. Okay, so the way this works is I'm going to put BB for Big Bang over here. Okay, and then what we say today, we're 10 to the what, 17th or something like that? Seconds. Okay. So it kind of goes this way, all right? So you kind of have to do that. So down here, we're talking about temperature. We said it used to be very hot, and it has cooled down. Now, even on this, I don't know what kind of scale this is, but 10 to the minus 10th. So that's 10 to the minus 10th seconds after the Big Bang. So that's kind of the way this works, 10 to the minus 10th seconds after the Big Bang. So finally then, we see once it's cooled down sufficiently, okay, we do have these four forces that we know and love today, okay? But going back in time, we had the electroweak, and then actually the strong force combined with electroweak to form what we call the gut force. And like, serious? Like Julia said, I couldn't think of her name. Like Julia said, gravity was the holdout. So that's kind of what we have going on.
So then, the forces have been changed over time?
The temperature changed, which allowed then the new forces, the forces to interact with the matter that was forming. All this time, as it's cooling down, energy is being converted into matter.
So do they know what elements were part of like the Big Bang? Because it was way hotter, so there are different elements, right?
And we're getting to this, yep. So even kind of down the road, and we're actually farther from this as it cooled down even more, even like the elements, like the periodic table elements.
That made up all the...
Yep, so basically when matter started being normal, and we're gonna call that at 380, is it million? Must be 380,000 years after the Big Bang, 380,000 years over here. It cooled down to basically finally get normal matter. So you have your nuclei, you have your electrons, you have your nuclei. And the elements that those were was mostly hydrogen, some helium, and some lithium. Maybe a pinch of beryllium. Okay, mostly hydrogen. Yep. Okay, so here we go. we're gonna chunk up, you're gonna see a timeline, and we're gonna chunk up what we know about different eras. Now, if you've studied dinosaurs, you know, like dinosaur eras, right? Okay, this is kind of the same thing, but eras associated with our universe as it was born after the Big Bang. And we're gonna start out first talking about those different forces, where they kind of entered in, and then we're gonna talk about kind of different particles, kind of mark the different eras. So starting with the Planck era. The Planck era. All forces, now this is going out on a limb, all forces may have been unified. I think unified was the word I was looking for, Einstein's looking for. Unified. So all forces, including gravity, may have been unified. So this is like, at the very top of this, you could put Big Bang. And here in a minute, you're gonna kind of see it unfold. So I put BB up here, and down here it's cooling, and it's more time. So that's kind of time flows like this. Well, after the Planck era, we have the gut era. Like, oh, that makes sense. Now, hopefully gut's ringing some bells. That's the three of the forces except for gravity. Gut era. Why, and this kind of goes back to what Ty was saying, so why now is gravity kicked out? Now we have these three forces together, and I guess it has to do with temperature and the amount of matter that's there in the interaction. But it's very, notice I've got like a 10 to the negative 43, and it might be hard for you guys reading in your slide, but 10 to the minus 43rd second is what we're talking about there. Beginning there. Okay. Now, if you want to underline inflation, you can. I don't know if that was a word that you had to, but inflation is a player in what they currently believe is the unfolding of our universe. Inflation basically is, I laugh when I say it, inflation basically is this is the fabric of space and time expanding as singularity kind of does its thing, okay, unfolds. So anyway, space and time expanded faster than the speed of light, basically during this what we call inflation. So there was this unfolding, and then there was inflation, and then there was the normal, okay? That's how it goes. That's how it goes. Okay, what else we got? Electroweak era. So hopefully kind of what I talked about before. Electroweak would be electromagnetic and the weak force are together, and what broke out was the strong force because gravity was already out. Why did it break down? It's cooling down. Okay, why did it break out? And you kind of see what time we're looking at, 10 to the minus 38 seconds, and you kind of see the associated temperature. So what else we got? Now we're going to switch gears from forces to particles. So the particle era, just the particle era. And again, we're looking at 10 to the minus 10 seconds, just called the particle era. You're like, well, what particles? Well, weird particles, how's that? It's still definitely not your average atom, okay? This talks about matter and antimatter, and again, you're like, that sounds so sci-fi, but it's true. And I'm thinking this Large Hadron Collider, they actually can see the antimatter formed. I'm thinking that's how that works. The problem with antimatter, it's very hard to isolate because if you get antimatter and matter together, they basically annihilate each other. And do they turn back into energy? I'm not sure, but they basically cease to exist. So there's a problem here. And what this says is that basically the proton, the normal proton, won out over the antiproton. This just totally floors me. So energy is converted to matter. Let's just go with protons. And there was just a little bit more. How much more? 1 in every 10 to the 9. So what's that? 1 billion? 1 in every billion proton was normal proton versus antiproton. All the other ones got annihilated. Yeah, you're like, are you serious? I just think that is so cool. And now, if you think, when you think of synthesis, what does synthesis mean? Like what?
How
Synthesis, like
How are we
photosynthesis,
supposed to think about the particle area?
combination, I think. What?
So there's equal amounts of antimatter protons and normal protons.
Almost. Normal
I
protons
think here
won
it's
out
supposed
just
to
a
be
little bit.
combination of two things like
There was-
synthesizing
One of those per every antimatter.
one thing.
One of those, there was like 1 billion and 1 billion and 1. And the 1 billion and 1 was the normal. And the 1 billion was the anti. I know. Yeah, I got to bring a documentary because you're not going to believe me about this. But I was after, I think I heard Jay say, this era, synthesis, I think a synthesis is putting together. I think I heard somebody synthesis. Like if you synthesize something in the lab, you're putting things together to make something. So era of nucleosynthesis would be making your nuclei. Okay. So nuclei began to fuse. Okay, so basically this says began when matter annihilates remaining antimatter, about 0.001 seconds after the Big Bang. No more antimatter. I just think that's so cool. The full-fledged era of nuclei was 3 minutes. Finally, I'm like, I can count 3 minutes. 3 minutes after the Big Bang, okay? You're talking about full-fledged nuclei forming. Now, when I think of a nucleus, we have protons. What else do we have in the nucleus? Neutrons, yep. So now you're talking about we must have neutrons available. Yep.
And there's anti-neutrons.
And there's what?
There's anti-neutrons too.
There are anti-neutrons. I'm pretty sure there's anti-everything. Yep. Yep. And this is a good place to finally get to. Remember this as I try to tell you way over here, I'm like, okay, so after the Big Bang, and I finally decided on, I think, 380,000 years. 380,000 years after the Big Bang, finally your electrons kind of find nuclei, like electrons associated with nuclei, and so the universe kind of clears up. It becomes what we call transparent. Before that, your electrons were like, dude, electrons are just running interference. It's still too hot for them to combine with nuclei. Want to cool down to this point, 380,000 years after the Big Bang, you could go ahead and get electrons to settle down, and then you can start to see the universe. Here it's opaque. I don't know if the word opaque means you can't see it. Okay, so anyway, that's a good place to stop. Because we have one more era, or a couple more eras. Okay? So just come, or I put that last one up there so it won't drive you nuts. If you need to fill in that, yeah. And then we'll start with Era of Galaxies Wednesday. So just come and see what we do. I don't know what we'll do.
Do you have the Edpuzzle code class code?
Yeah, but there's nothing up there to look at right now.